My name is Ashley Lawson, and I'm a senior fellow here at the Center for Climate and Energy Solutions. I'll be your moderator for today's webinar, Connecting the Dots Between Climate Change and Extreme Weather. It seems like there's always an extreme weather event in the news. Today is no exception, with a lot of news coverage of the fires happening in Northern California. For those of us working in climate change, these sorts of events usually cause someone or other to ask us, hey, is this because of climate change? So I imagine that many of you here today get those questions either in your organization or even in your personal life. So today what we're going to do is go through the facts and what is known about the connection between climate change and extreme weather. Hopefully by the end of the webinar today, each of you will be armed with new information that you can use the next time the weather gets a little weird and someone asks you about climate change. Before we begin, though, I'd like to review a few housekeeping notes with you. This webinar is being recorded and will be posted to our website, c2es.org, in a day or two. Because we have so many people attending, we're going to keep everyone's line muted. If you do have a question that you'd like to ask our presenters, please use the GoToWebinar questions feature in the control panel. We'll do our best to get to everyone's questions today, but I can't promise we'll have time for them all. If you have any clarifying questions about the presentations, I'll ask those at the end of each speaker's remarks. And if you have a question that's for general discussion, I'll save all of those for the end. So here's our agenda for the day. I'm going to introduce you to our terrific panel of experts and also take a few minutes to better introduce you all to C2ES and our work. Then we're going to dive into these questions with the aim of connecting the dots between climate change and extreme weather. We've ordered things so that we'll start at a high level with an overview of the different mechanisms involved, and then we'll get progressively more granular and more complex as we move through an overview of some observational data sets and some new scientific advances. As I said, we're saving some time at the end for questions, but feel free to send those our way at any point in the webinar. You don't need to save all of your questions for the end. So here are the presenters for today. As I said, my name is Ashley Lawson. I'm at C2ES, and I'm going to kick us off. I'll then turn it over to Deke Arndt, who is the Monitoring Branch Chief at the National Centers for Environmental Information, or NCEI, at NOAA. He is going to share much of the data that NOAA collects and monitors with the observations of the climate in both the US and globally. Next, we'll hear from Adam Smith, who is also joining us from NCEI. He leads the project that gives us the estimates of billion-dollar disasters. So these are the natural disasters that occur in the United States that result in $1 billion or more of losses. This data set is familiar to many of us working in climate, so we're really glad that Adam can be here to walk us through the details of how that data is collected. And then lastly, we'll hear from Michael Wehner, who is a senior scientist at Berkeley National Lab and an expert in the field of event attribution. He's actually experiencing the public health impacts of those Northern California wildfires firsthand, so a timely topic to be talking about. We're going to make sure to keep our fingers crossed that his voice holds out from the smoke inhalation that he's been doing lately to share some of his advances in terms of event attribution and understanding what it is that we can say about specific events. So for those of you who aren't as familiar with C2ES, we are an independent, nonpartisan, nonprofit organization. We've been working on climate change and clean energy policy since 1998 with the mission to forge practical solutions to both reduce greenhouse gas emissions, expand clean energy, and strengthen the resilience to climate change impacts. Central to us is the belief that businesses should be part of the conversation about climate solutions. We work with many businesses, both large and small, but a key set of partners for us are the companies who are members of our Business Environmental Leadership Council. All of the views of C2ES are independent from the views of these companies. However, they are, as I said, partners for the work that we do. I'm going to be keeping it very short today in terms of coverage of information, but there is much more information available on our website, covering everything from the basics of climate science to policy options for greenhouse gas mitigation and adaptation to climate change, to examples of business leadership. So please do use the resource, this website, rather, as a resource for your own work on climate change. With those introductions out of the way, let's move into some of these scientific questions. So first off, why and how do greenhouse gases affect extreme weather frequency and intensity? So maybe I should start here with what is the difference between climate and weather. Climate is a term we use to talk about the long-term average temperature and precipitation conditions for a place. When talking about climate, you have to use statistics and probabilities. Weather, on the other hand, is the term for the temperature and precipitation conditions that we can observe just by looking out the window today. Climate change can influence weather norms and extreme weather, and here's how. The release of greenhouse gases into the atmosphere has a warming effect as more heat is trapped into the atmosphere. That, in turn, causes land and ocean temperatures at the surface to increase. Those increasing surface temperatures are the direct impacts of climate change that are the easiest to measure and for which we have the most confidence. But that warming has secondary impacts, like increased moisture content in the atmosphere and the melting of sea ice. Then there are the implications that those secondary impacts have themselves for extreme weather, like heat events, thunderstorms, rain and snow events, hurricanes, drought, all the rest of it. Climate change will make some of these kinds of events more frequent. They'll happen more often than they used to. And other kinds of events will become more intense. They'll be stronger or longer in duration than they used to be. And some events, like heat waves are an example, those will happen both more often and they'll be worse than they used to be. So a major area of research right now is understanding in which of these ways climate change will influence extreme weather. For example, the impact of warming on tornado frequency and intensity isn't well understood. Those are just question marks for us. So those are, in general, the steps in the mechanism by which climate change influences extreme weather, and I just want to go through each of these steps in a little more detail. Fundamental to all of this is the greenhouse effect. So this is not really a controversial area of science. These physics have been well understood for a long time. The greater the concentration of certain gases in the atmosphere, then the greater the amount of energy that is held close to Earth. And the more energy held close to Earth means higher temperature. By the way, though, the physics here aren't actually the same physics that are in place in actual greenhouses. So we're certainly not going to try to change the name of an entire field of study, at least not today on this single webinar. But I did want to make clear that greenhouse gases don't actually act like a greenhouse. They act more like a blanket. So putting more gases into the atmosphere is like throwing on another blanket. More of the heat that you're giving off comes back to you, and you get warmer. We know that greenhouse gas concentrations are increasing because we can measure them pretty easily, and we know that temperatures at the surface of the Earth are increasing too. So this map is from the 4th National Climate Assessment, which came out just last year. For anyone not familiar with the National Climate Assessments, these are periodic reports that the federal government is required by law to produce, and they assess changes in the global climate. Numerous federal scientists at different agencies work together with academic researchers and other experts to review the literature and synthesize all of that scientific information. The National Climate Assessment, or NCEI as we call it, is similar to other assessment reports you may have heard of, like those coming from the IPCC. And that similarity is that the NCEI doesn't produce new science. Rather, it reviews scientific research and makes determinations about confidence and certainty of different findings based upon the level of understanding and agreement in the field. So these observations of increasing temperature are known with very high confidence. Temperature is easy to measure. We can measure it from satellites, and we've been watching temperature from space for several decades now. Actually, since before many of us on the line today were even born, for what that's worth. This map shows the change in degrees Fahrenheit since the first half of the 20th century. Again, since climate is measured statistically, and we want to avoid comparing individual years because the weather will, of course, be different each year. This is actually the average from 1986 to 2015 compared to the average from 1901 to 1960. When you look at different data sets, you'll find slightly different values for the recent increase in temperature, sometimes because the global averaging methodology is different from data set to data set, and sometimes because the time ranges used for comparison are different. But they all agree that warming over the last century or so has been about a degree. It's easy to see on this map an important caveat about that 1 degree number, and that's that it isn't the same everywhere on Earth. The Arctic is warming faster than the rest of the planet, and land areas are warming faster than the oceans. Since few people live in the Arctic or in the middle of the ocean, it's tempting to think this is a beneficial effect, but as we'll discuss more today, the Arctic climate is terribly important at influencing the climate of the entire planet. So the Arctic amplification, as it's called, the excess warming happening near the poles, is actually a huge source of concern. So what are the impacts of this warming? Surface warming can directly affect some types of extreme weather. Heat waves and daily temperature highs are increasing. That's what the bar chart on the left shows, again from the NCEI. That's not much of a surprise. If average temperatures are increasing, then you would expect maximum temperatures to increase too. The bar chart here shows you daily high temperatures. That's how hot does it get in the middle of the day. But another impact that's very important for public health, but not shown here, is that nighttime temperatures are increasing too. So daily low temperatures are warmer than they used to be too. Warmer air isn't just hotter, it's also wetter, and that's what the map on the right shows. You may have heard of the Clausius-Clapeyron equation, which describes the relationship between temperature and moisture in the air. Not only can air hold more water as it gets warmer, it can hold exponentially more. When all that water condenses out, you get more rain or more snowfall, depending on the temperature. So extreme precipitation events are more extreme than they used to be. This is, again, an impact for which the mechanism is well understood and the observations are robust. So we know with high confidence that heavy precipitation events are increasing in both frequency and intensity. Rain and heat are important weather events, but they don't make news headlines the same way that other sorts of events do. Rare events like hurricanes, or more generally tropical cyclones, capture our attention. And as we saw this fall with Florence and Michael and other recent hurricanes too, they can be devastating when they make landfall. However, precisely because tropical cyclones are rare events, we don't understand them as well as heat waves. And so there is less confidence in identifying changes in frequency or intensity. We're going to come back to this question today, and I won't steal the thunder from Michael. But I did want to set the stage by walking through the mechanism by which climate change could influence hurricanes. So this part, again, is fairly well understood. Warmer oceans give more energy to tropical cyclones, which can make them stronger in terms of wind speed and overall energy. But where there is more debate and uncertainty is whether this change is already being felt today, although we do have strong and clear expectations that it will be felt more in the future. So global warming, and in particular the greater warming happening in the Arctic, or really at both poles, has the potential to change the very large-scale atmospheric circulation patterns on Earth. These patterns influence weather. For example, they determine which regions of Earth stay dry and form deserts. Have you ever noticed on a map that most of the world's deserts line up with each other at roughly 30 degrees latitude, both north and south? So this map is only showing you half the Earth, but if you look at a full map, you'll see that the Arabian Desert, the Gobi Desert, and the deserts of Australia all also more or less line up with the deserts shown here. They're colored light brown in this picture. That's not by accident. It's because of the position of a large-scale atmospheric feature called the Hadley cell. Model results and theory suggest that the Hadley cell can expand with warming. That is, it can stretch out farther from the equator. This could cause currently humid regions of the Earth, which are also the places where we live and grow most of our food, to become more arid. The other large-scale feature I'll mention today is the jet streams. So where the jet streams lie on Earth and the shape of the jet streams have a strong influence on local weather. Again, models and theory suggest that jet streams will change with warming in such a way that droughts, floods, heat waves, and yes, also cold waves can actually become more common. But note that I've given stronger caveats on this slide than the others. So there's still low confidence that we're seeing these changes today, and the mechanisms for these changes are still being investigated and debated. The conclusions I'd like to leave everyone with right now is that climate change can and does affect the weather, at least some types of weather today. We have the most confidence in changes in the kinds of weather that are directly related to temperature and that are pretty common, so heat waves and heavy downpours. But scientists are still working to better understand rare events like hurricanes and complex events like droughts are one. So we're going to move now into a greater level of detail with some of the other speakers that we have. I'm going to conclude the remarks that I have and turn it over to Deke.
Thank you, Dr. Lawson. My name is Deke Arndt. I'm from NOAA's National Centers for Environmental Information. We're headquartered here in Asheville, North Carolina. We were formerly known as NOAA's National Climatic Data Center. Still the same stuff, and I'm going to provide a little bit of context for the kind of more detailed presentations following by Adam and by Dr. Wehner. So next slide, please. Just as a brief commercial, where the perspective that I'm coming from, NCEI is basically the world's weather and climate data library. So this graphic represents observations from years past being merged with observations from yesterday in this basically data center located here in Asheville. We do have the benefit of several centuries of weather and climate, and particularly paleoclimate observations in our campus. And we use this instrumental record and even the pre-instrumental record to try to glean signal from what we've observed. Next slide, please. And I apologize, one more slide, please. So there are three main sources that are going to underpin some of my comments today. One of them is the State of the Climate Report, which is published annually in the Bulletin of the American Meteorological Society. This is a publication that's led each year out of Asheville, out of NCEI here, and we have about 500 authors from about 60 countries that contribute several hundred sections, each dealing with a different piece of the climate system. In addition, I'll be drawing on a series of articles that were published in the Bulletin of the American Meteorological Society over the last 5 or 6 years that articulate the known and unknown about the relationship between changing climate and certain high-impact weather extremes. Next slide, please. Much of this will come from the National Climate Assessment, and Dr. Lawson already gave an overview of what that publication, that assessment activity attempts to do, which is synthesize what is known in a coherent way, ascribe statements of confidence to what is known. I'll be drawing both from the 2017 science update that precludes the release of the larger assessment report here late this calendar year, and I'll also be pulling back to the 2014, the previous kind of official full-blown report as well. There are some very subtle differences between what was known then and what is known now, but largely the big picture is the same. So when I say the NCEI, I'm referring either to the recent science update or the last official published report in 2014. Next slide, please. And then finally, some of the data that we'll show today comes from the operational monitoring that we do here at NCEI. We provide many of the constituent data sets that go into these kind of higher ordered scientific assessments. We do what in climate would be called real-time monitoring, so like a play-by-play of the climate system, what happened, how unusual was that, how does that fit into recent trends or expectations in the future. We don't pursue in our group climate attribution, which Dr. Wehner is going to talk about, but we essentially do a lot of the scorekeeping of the climate system and develop products and data that feed into these higher ordered assessments. Okay, with that out of the way, let's hit the next slide, please. Okay, so one thing that we, probably our most visible product in a changing climate, just to zoom out to the planetary scale, is the global surface temperature. It is indeed increasing. Any major institution that tracks global temperature, and we're just one of a handful of groups that do so, their data sets are singing the same song. We may be hitting a few different notes along the way, but the general picture is the globe is warming as we would expect it to warm in an increased greenhouse gas world. Each one of the red circles on this graph, reading from left to right, which is 1880 through last year on the right, represents how much warmer or cooler than the 20th century average that year was. So years, red circles that are above the black line represent years that were warmer than normal or warmer than that 20th century average. Red circles below the black line represent years that were below the 20th century average. And the pink bars represent just simple decadal averages, the average of the 10 years in that decade. And so you can see a few things going on here. One, the trend is inescapably up. We are warming as we would expect to warm. There is year-to-year noise, so some things happen within the climate system and within the weather patterns that cause some jumping up and down from year to year. But overall, the trend, especially since the middle 20th century for global temperature, is we're riding an escalator up. We're getting warmer over time. Those decadal averages are clearly pointing up. The year-to-year averages look like we're jumping up and down while we're riding that escalator up, and that's exactly what we're doing. The recent 4 years have been the 4 warmest on record. We are basically, with each decade, approximately kind of in a new neighborhood of global temperatures. So far, we're on pace to be the 4th or 5th warmest year on record for 2018. That will share a top 5 status with the previous 4 years. All right, next slide. Okay, so looking again, this is the last, I think, big picture slide that I'll touch on. This is from the previous National Climate Assessment, and it shows the rate of warming in the contiguous United States and Alaska and Hawaii since the middle 20th century. And you can see that, as Dr. Lawson showed, much of the U.S. is warming at or greater than the planetary rate. There is an exception in the Deep South, this what is kind of dubbed the warming hole. There are competing explanations for why the South is not warming as rapidly as the rest of the country, and those competing explanations range from more moisture, more precipitation, more cloud cover from a warmer Gulf of Mexico to chance. And so again, the point of this slide is to show that for the most part, the U.S. is warming kind of in step with the rest of the world, particularly at the mid-latitudes. All right, next slide, please. Okay, so finally looking at some data. This is from our Climate at a Glance product, and this is through the year 2017. And this is kind of an eye test, but the details, the individual details aren't so important as the big picture. So what you see in the left half of the screen are individual months in which a state in the U.S. Set its record for that month, warmest, coldest, wettest, or driest. So there's a lot of red, which means we've been establishing new monthly average temperature records through this decade, and this is since 2010, basically, through 2017. A lot of red, a little bit of blue, quite a bit of green, indicating that some prevalence of setting wettest month on record or wettest September on record, wettest October on record, and so on, and a little bit of brown as well. The two columns on the right are the same concept, but instead of individual months, we're looking at seasons and calendar years. Again, the individual details themselves aren't as important as the big picture here. The big picture is we see a lot of red. We still see some blue, but not very much of it, indicating we are not dipping into record cold values nearly as much as we are on the warm side. And we're seeing quite a bit of green on there as well, indicating excursions to unprecedented wetness at the state level anyway, at the month and seasonal time scales. Again, this is context for or a follow-up on what Dr. Lawson pointed out, in that as we push the temperature spectrum to the warm side, the kind of constellation of temperatures that we see in this warmed climate versus the climate of 50 years ago, as we push that to the warm side, we are biting off new territory with record warmth, and we have a graph that will show that shortly. Next slide, please. Adam Smith is going to detail all of this, but the point of the last slide was to show that we've experienced many extremes just in this last decade, even at the monthly scale, even before we start talking about individual events. Adam's going to detail what goes into this billion-dollar weather and climate disaster product, but I just wanted to point out that we are seeing an increase in these as well. And so the combination of the last slide, the big events that we've seen this year in particular and the previous year, those are, often come with the question, how is this related to climate change? And so next slide, we'll talk a little bit more about that. Okay, so I apologize for the literature review, and don't mean to be flippant here, but I can't think of a better way of articulating the relationship between weather and climate. We spend a lot of unnecessary energy in my discipline trying to separate weather from climate, and the fact is they are very related. Climate is the context in which weather happens. It's the context in which big weather happens. So I'm dating myself a little bit. I'm one of the people that was born was alive when satellites came around. But if you think about the relationship between weather and climate, weather throws the punches, and we're talking about big weather here. Climate trains the boxer. And the relationship is that, we don't know what individual punch Rocky's going to throw with 2 minutes and 12 seconds in the 7th round of his next fight. That'll be determined by what's going on at the moment. But we do know that if we change the trainer, that he'll be throwing a lot more left hooks. He'll be throwing some punches more often, some punches less often, some punches more effectively, some punches less effectively. Again, like Dr. Lawson said, statistically over time this plays out and signals get clear. So there's this coach-athlete, mentor-apprentice, teacher-student, however you want to define this relationship of long-term influence from a changing climate to big weather. All right, next slide, please. All right, to kind of abuse the 20th century pop culture a little more, I just to reinforce this relationship, and Dr. Wehner is going to provide some details in the attribution world. I have a teenage boy. He's very much like you would describe in this column on the left. He's an impulsive guy, has a short attention span. He can be very sensitive to things immediately around him. If the right set of ingredients come together, he could do extreme behavior. The beautiful thing about him, he forgets quickly and moves on. And if we hadn't named it something else, we could have called him weather. This is a description of weather. Next slide, please. And that's in a stable climate, right? So these ingredients that cause extreme behavior, whether it's in a teenage boy or whether it's in the weather and climate system, even in a stable climate, these ingredients come together. Next slide, please. But if you change the climate, if you change that parental long-term influence, and I think this is important for almost all of the big weather phenomena that we deal with, the weather is still the weather. The ingredients that make the weather extreme are the same ingredients that make the weather extreme 50 years ago. In a changed climate, just like my teenage boy is still going to be impulsive, he's still going to respond to the things immediately around him. It's the way the ingredients come together to make his extreme behavior is going to change. And again, in a changed climate, it's the frequency and the magnitude with which these big weather-making ingredients come together that are changing the trajectory of things, even if the ingredients themselves, to point to this week's events, this month's events in the West. Wildfire in the West is driven by high winds, low humidity, drought, and stressed vegetation. Those are the ingredients for a wildfire. Wildfire events tend to have a combination of, if not all of those events, those factors going on. What climate does is it changes the frequency with which they can come together. It changes perhaps the duration of the season in which those conditions are prevalent. It perhaps changes the timing of the event or the intensity of a single one of those ingredients, such that the event can become more intense. And we'll look at some examples right away here. Okay, next slide, please. Okay, so just as an overview, this was a series from earlier in this decade where we tried to quantify and characterize what we know about big weather versus climate change and what we can detect. And on this graphic, there's a series of articles on the left. On the graphic on the right, as you go from left to right along the axis there, that indicates that we are essentially better at observing and detecting signal on whether these big events are changing. And as you go from the bottom to the top on the axis on the left side, as you go up, that indicates at the time our confidence in our understanding of the physics and the dynamics that are driving these events. And to very little surprise, it tends to be that the things that we observe the best tend to be the things that we know the most about. So the things on the upper right are well observed and they're documented. And so precipitation, heat waves, cold waves, flood and drought to some extent tend to be the things that we feel we know the most about and we do know the most about. And they're also the things that we can observe changes the best. As you go lower to the left, the short-lived phenomena that are difficult to observe, like ice storms because they're very rare, thunderstorm winds because they're a very small scale, they happen in minutes and take place over a handful of miles, as opposed to the climate changing over decades, and it's a planetary thing. So you see these things at play. I'm going to focus more on the stuff kind of in the upper right, the things that we know the most about here. But if you're interested in quantifying the relationship, at least as of about 3 or 4 years ago, these are wonderful articles. All right, next slide, please. So in a warming world, this is theory here. I described this earlier, so I won't spend too much time, but the left bell curve would have been, say, the climate of the recent past. Just imagine it as the 20th century climate. And there's a distribution of temperatures in that climate. And most of the temperature kind of hangs out in the middle of the distribution. That's the hump in the bell curve. And to the left, shaded in blue, is what was at the time described as extreme cold. And to the right, a little piece shaded in pink was what is at the time described as extreme warm. With climate change, you're heating that population of temperatures. You're moving that entire distribution to the warm side. So the bold bell curve on the right tends to leave behind what used to be called extreme cold. It has become even rarer in the new climate. And that larger section of pink underneath the curve is what used to be considered the extreme heat event, is now much more part of the picture in the new climate. So much more pink underneath that right curve than there was under the left curve. And then the dark red area basically represents new unprecedented temperature outcomes that basically did not happen in the previous climate. This is theory, and if you click one more time, the observations bear that out exactly. So going from upper left across the top, the upper left panel is a distribution of temperatures from the 50s, 60s, and 70s. Upper right panel is the 80s. Lower left is the 90s. And then the lower right is the first decade of this century. And you can see that, with a little bit of noise that we see typically in observational empirical studies, we are realizing the theoretical change. These are summer temperatures in the northern hemisphere, by the way, but we can see as we hold that 50s, 60s, and 70s curve in the green dotted line that the curve is pushing farther and farther to the right, to the warm side, such that a big heat event is much more likely now than it was in the middle 20th century. Next slide, please. And then finally, as Dr. Lawson kind of intimated, this is 2016 high and low temperatures. The numbers, again, aren't as important, but I wanted to emphasize something that she brought up, is that in general, the minimum temperatures, if you look at the 3 to 4 ratio, we are seeing minimum temperatures increase a little more rapidly than maximum temperatures. Minimum temperatures being the morning time or overnight temperatures, maximum temperatures being the afternoon temperatures. So in general, in a kind of a 3 out of 4 sort of way, we are seeing low temperatures warm more than high temperatures. We are seeing low temperature extremes. We're seeing very warm morning low temperatures increase more rapidly than afternoon highs. And the next slide will show kind of re-emphasize that. This is from our Climate Extremes Index. This is summer morning time temperatures in the U.S. from 1910 on the left through the summer of 2017 on the right. What this graphic shows in blue and red is the amount of the U.S. that experienced extremely cool or extremely warm summer minimum temperatures over the 20th century and part of the 21st century. And you can see that the last few decades are definitely more of the U.S. experiencing extremely warm morning temperatures, even after accounting for the fact that it's summer and the place. And we're seeing 2, 3, in some years 6 times as much U.S. territory subject to what used to be considered extremely warm minimum temperatures. A morning time temperature of 79 in the summer isn't quite as sexy on TV as an afternoon temperature as 104, but it can have more profound economic impacts in terms of energy demand, people running their air conditioners longer through the night. It can have public health consequences, especially for an outdoor labor force, and it can have agriculture and horticultural stress consequences as well. So in a lot of ways, summer morning time temperatures can be as important or more important than afternoon temperatures. And we're seeing clearly a trend up. 2018, by the way, set a record. We had to adjust the labels on this chart as it exceeded 6 times the expected amount. All right, next slide. And then this is the last data slide. This is from the National Climate Assessment, the previous one. Big rain, as Dr. Lawson said, a warmer atmosphere can carry more water vapor to a storm, which can deliver more rain or snow when the weather makes that happen. And we are seeing, especially east of the Mississippi, an increase in big rain in kind of 2 dimensions. One big rain, the biggest events are getting bigger. That's kind of the simpler dimension. The second dimension is that big rain events, big 1 and 2 day precipitation events, are becoming more responsible for the total amount of rain that we get in a year. So proportionally speaking, that bucket that we fill up each year with precipitation is being filled more and more by these big single rainfall events compared to the past. And that has important consequences, obviously, for flooding, for runoff, for water quality. It also has consequences for what do we do to store all of this water that falls at once? Do we need to reimagine our reservoir operations or our reservoir infrastructure to handle this reality, especially east of the Rockies and especially east of the Mississippi, that the distribution, the dosing of rain is becoming much more tilted towards the very heavy events versus less of a prevalence of the medium-sized events. All right, next slide, please. And then finally, just to wrap up, and Dr. Lawson had already hit on this, what extremes are increasing? Big heat is definitely up, clearly, and that's clearly in line with expectations. That has to do with both the magnitude, the frequency, and the duration of big heat events. They are clearly up. Big cold is down. So again, as we push that bell curve away from the cold towards the warm, we're leaving where big cold is down, statistically speaking. Big rain is up in both of the dimensions that I mentioned earlier. There's a clear signal, but perhaps less so. A big drought is up. This is especially true for the western U.S. And that we're seeing the West more prone to drought in recent decades than before. For tropical cyclones and hurricanes, again, we are seeing more of them. The fact is we're better at observing them. That's probably why we're catching more of them. So there isn't much increase on whether we're seeing or will see more hurricanes. There is fairly good consensus that the hurricanes and tropical storms that we get are going to be on the more intense end of the scale. So we'll see more intense hurricanes. They are operating on seas that are higher than they were. So storm surge, even for the same storm 50 years ago versus today, storm surge has several inches added onto it. A recent study that came out in Nature by several colleagues of mine, in particular one from NCEI, showed that Northern Hemisphere tropical storms are slowing down, tend to be a little slower. That's not good in a landfalling tropical cyclone situation because they can dwell more in a place and deliver more rain. And then we have these other kind of things to do with very short-term events where we don't have a clear signal for snow and ice storms and local winds and hailstorms. And next slide, please. I believe that's it. Yeah, and I will hand off, I believe, to Adam Smith to talk about billion-dollar disasters.
Before you do, though, we had a few questions come in, just some clarifying questions about your presentation, and I also have to thank you for introducing some new analogies for us to talk about how climate change and extreme weather interact. I love the idea of teenagers being teenagers, but their home environment is going to influence the way that they act out. I have been using the performance-enhancing drugs analogy in baseball for a long time, but that's starting to feel dated. So it's nice to have a new good analogy out there. One of the questions that came in, Deke, was asking if you could describe in a little more detail the methodology that you use to calculate the global surface temperature. So back to one of your earlier slides, I don't know if we're going to be able to push all the way back to that, but the one that shows the global average temperature record. Can you just talk through some of where that data comes from and how you can take it all and turn it into one red circle on your chart?
Sure. That's taken largely from three sources over land. It's basically the Meteorological Services historical weather observing stations. So over land, if you imagine the National Weather Service having a fleet of automated and volunteer-operated observing stations and kind of extrapolating that over the 180 nations that contribute to the World Meteorological Organization data sharing protocol, that comes from basically weather stations. Over the oceans, we have a combination of ship observations, which come from both military and commercial shipping operations, and then we have increasingly, especially in recent decades, buoy observations, so moored and drifting buoys that take the sea surface temperature. And we combine these. What we do, generally speaking, to save time for the coming speakers, we calculate for any given month, that month's, so imagine the weather station in Columbus, Ohio. So for the October 2018 observation, there would be a monthly average. We would subtract that monthly average from the long-term average from something that we would call normal, and we are left with the residual that we call an anomaly or a departure. And we take all of these departures and then kind of recombine them on a grid, kind of in a specified way, and we technically calculate a global temperature departure using all of these ship, buoy, and weather station observations. And that global temperature departure is the calculation we make, and then we map that back sometimes onto the global average temperature, but we prefer to operate in that departure space. So that was a little veering. I hope that was adequate for your question. We've done. We can come back if you'd like, if your audience would like, and do a more detailed, kind of thorough description of how we do that.
Thanks. Yeah, I think that does give a good sense that there's a lot of effort that goes into what, at the end of the day, looks like one single number that many of us talk about on a daily basis. But it's helpful to understand the vast number of observations and work that goes into that. Another question came in about how do we mesh these two ideas. One that I talked about, that with warming at the poles, you may see a change in the extent of the Hadley cell, which could bring aridity to new regions of Earth, particularly the southeast of the United States. And then the chart that you showed, that I believe I can go back to fairly easily here, yeah, this one that is showing the percent increase in rainfall. So the question was about, are we seeing drying in the southeast, or are we seeing increased precipitation? I suspect that the answer to that, or what might help clear it up, is that this chart is not showing annual totals. But can you just confirm that and maybe tell us one more time what this data is and the numbers on this chart?
Yeah, thanks. So this chart is showing essentially the relative role of the very largest precipitation events as contributors to the annual rainfall budget. So it's not showing an increase overall in the total precipitation that we see in the region. It's showing the increased importance of very large events to their annual totals, kind of averaged over the region. In general, we are seeing changes in precipitation, generally slightly up, but regionally and seasonally, it is diverse. It is not all moving in the same direction. But what we are seeing generally moving in the same direction is that regardless of what region you're in, and regardless of how much your total precipitation is going up, or in some cases slightly down, the relative role of very large events is increasing, is becoming much more important in the overall precip budget.
Great, thanks for that. And thanks to our audience today for your questions. Keep them coming. We love to know what you are interested in, and we'll do our best to answer those questions along the way. I am going to turn it now to Adam, who's going to continue down this road of complexity that we have. So what is the theory of what greenhouse gases do for weather? What do we actually see in the weather? And now this is really a question of, what does it cost us? So Adam, over to you.
Hi, thank you. So yes, today I'm talking about these major disasters we've explored over the last 39 years in the United States, regarding the sources we use, the trends, the costs, and some mapping that I often encourage people to explore on our interactive website. Next slide, please. So here is a brief outline on what I will go over today. First, some context for what we're trying to measure. Second section is the public and private data sources and what we're trying to measure. Third section regarding the last 2 years in review, because we've had so many different types of weather and climate related events in the United States, briefly highlighting some of those. And the fourth section, it's my favorite. I think it really provides the context and depth regarding which disasters are changing fastest, cost the most, and what parts of the country are being impacted the most. Next slide, please. So I'm privileged to work with Deke at NOAA's National Climatic, or NCEI rather, and we have many products that essentially are trying to understand trends and anomalies for a variety of weather and climate related variables. And as part of this responsibility, we, since 1980, have analyzed what we call billion-dollar weather and climate disasters. And it's important to note that, as Deke had mentioned before, these disasters are in fact increasing not only in the physical variables, but also we're seeing that impact on the ground. From 1980 through 2000, we see that these billion-dollar weather and climate disasters roughly constituted 75% of the full distribution of weather and climate-related event losses at all scales in the United States. And this includes sub-billion-dollar disasters, which we every year update through inflation-adjusted means. So we're trying to capture that distribution as it shifts forward in time. If you look at 1980 through 2010, the percent of the full distribution of losses that were in relation to only the billion-dollar disaster events jumped from 75 to 80%. And of course, in the last 2 years, in particular with hurricane impacts, we see now that this full distribution, the billion-dollar disasters captures about 85% of the full distribution, which is roughly 1.59 of $1.88 trillion in losses. And all of the figures I will be highlighting today are adjusted to present-day dollars using inflation. Next slide, please. So there's certainly many different ways you could tackle this. It's a challenging, complex problem. So on the left side, you'll see that we have a variety of different disasters, or perils, as some people call them. The ones we do not focus on for this particular product are the geophysical events, including earthquake, tsunami, or volcanic eruption damage. But so the green boxes in the center of this slide highlight where the best public and private sector data lies, and so that would be public and private infrastructure, business, and other property means, which I'll get into in the next slide. But the purpose for this is to highlight how, in fact, there are many parts of a disaster that are not adequately measured in the purple and the blue boxes, just by virtue of the fact there are not good long-term data sets that are consistently available. But let me go into more detail in the next slide, please. One more slide. So this slide shows that what we're trying to do requires a broad array of public and private sector data. And really, the focus is to capture the best data we can, and then caveat what we're not trying to capture. So you can see that in the black, the X's denote the interface between the different types of public agency data or private sector data, and then the perils. So the 7 perils that we assess include hurricanes and tropical storms, severe local storms, which would be tornadoes, hail, and straight line wind damage from convective storms, winter storms, crop freeze events, wildfire, drought and heat wave events, and then non-tropical inland and riverine flooding events. And from all this data, we seek to capture total direct losses, which are the insured and uninsured losses for many different assets, including physical damage to residential, commercial, and government buildings, all the content within those buildings, of course, time element losses such as business losses, which can really add up after a hurricane, vehicles, boats, offshore energy platforms, public infrastructure, which is very important to get us, a city back on its feet, the damage to that, and also the agricultural assets, crops, livestock, and commercial timber. But I think it's also important to highlight what we do not capture due to lack of data, which includes natural capital losses, mental and physical health care related costs, which are substantial, but we just cannot assess that, and the statistical value associated with loss of life. So I think the takeaway is that these losses actually represent a conservative measure of what is truly lost, but we cannot fully measure from after these events happen. Next slide, please. So I won't spend too much time here, but for future reference, this is some metadata behind all these loss data sources. So I highlight the FEMA National Flood Insurance Program, USDA's crop insurance, the U.S. Army Corps of Engineers, the National Interagency Fire Center, and on the private sector, the Property Claim Service, which is really a gold standard source for insured property losses from many variables. And I think it's often underserved that state agencies provide a valuable source of context on the ground during and after disasters. For example, the CAL FIRE agency provides excellent information for the wildfires that are happening in California. So that's just an example of all of the information we are putting together. And one of the initial transformations for all of this information is initially to scale up the insured loss data by the reciprocal of the insurance penetration rate. But all of this, of course, differs by disaster type, by geography, and asset class. And there's several steps we go into this process to understand the cost. Next slide, please. One more slide. Thank you. So last year, many of you may have seen this map. This is our media-friendly map, basically showing the center of these different billion-dollar weather and climate disasters. And last year, in 2017, was indeed historic, not only for the number of events, not only for the cost, but also for fatalities. So there were 16 separate events, total costs slightly above $300 billion. And sadly, with the study done in Puerto Rico after Hurricane Maria, over 3,000 fatalities. Those are all records or tied for records in our database. And the two key reasons why 2017 was historic was, of course, the damaging, devastating wildfire season last year in California, which we're seeing again this year, and of course the hurricanes, which both of those were new annual records for the United States. In fact, the wildfire season last year in 2017 tripled the previous U.S. annual cost record, which had previously been back in 1991 at an inflation-adjusted $6 billion. Last year was $18 billion. I don't think this year will be very different from last year as far as costs, already looking at the number of structures that have been destroyed. Next slide, please. So here is it's already dated version of the media icon map, as we call it. You can see it does not have Hurricane Michael because that happened in early October, and this is a quarterly product. So this was our Q3 release. But not even counting Hurricane Michael, we had already experienced 11 different events in 2018. So Michael would make that 12. Total costs, I'll highlight that in a bit. That's still, of course, to be determined. We're collecting data on that each day. And so the events of this year were 6 severe storm events, 2 winter storms, a pair of tropical cyclones, and of course a drought and the wildfire that's really plagued the West. And all of this will be updated in our 2018 Q4 update, which happens the first week of January. Next slide, please. So getting into more of the data, as Deke expertly highlighted, we are seeing more of these events, and there's a combination of factors. Certainly there's more exposure, which means there's more vulnerability, but also for certain event types, climate change is increasing the potential frequency, perhaps longer wildfire seasons out west, or we're seeing more frequent inland non-tropical flooding events. In fact, the blue events you can see from 2000 to present, and the bars, those are the non-tropical flood events, and we've had quite a few of those. So indeed, these bars reflect each annual frequency count for billion-dollar disasters, color-coded by event type. The black line is the 5-year running average for costs, and then the spiky grayish line is the annual cost for these events annually, again, all adjusted for inflation. And as you can see, 2017 really stands out above, head and shoulders above the rest. 2005 would have been the second costliest year in our period of record. Of course, that's Hurricane Katrina and the hurricane season of 2005. And the year 2012, we had Sandy and the historic 2012 drought, among many other events. So those were the three costliest years in the last 39 years. But as I mentioned, we will be adding Florence, Michael, Western wildfires, and the Western drought, the cost for that in Q4. Next slide, please. So this shows the same type of information, but in an annual calendar, January through December. And so you can see how the progression of each year back to 1980, how the frequency of events has changed. So the black line is the annual average for the last, from 1980 through present, which is about 6 events per year, including many events that have been inflation adjusted to present dollars. But I think it's more important to look at the last 5 years when you're really trying to add context. So from 2013 to 2017, it's nearly twice the frequency at 11.6 separate billion-dollar disaster events each year in the last 5 years. And the red line, as you see, is this year. And so Q3 is our last update. So I'm just denoting that will increase, of course. And so it's clearly going to be a top 4 year as far as frequency. The top years were last year, 2017, which tied 2011. Many people will remember that was a very active year for severe weather and tornado outbreaks, and we had 2 major inland flood events, among many other events. And then 2016 actually gets overshadowed by 2017. 2016 was actually quite a historic year as well. In fact, we had $4 billion inland flood events that year in 2016, and the previous annual record had been 2, so it doubled the previous record. So again, lots of different extremes changing in different ways. Next slide, please. So this is the same type of setup, except for it's not frequency, it's cost. So you see, again, last year, 2017, the purple line set the new standard as far as costs, over $300 billion, eclipsing the 2005 line with Katrina and the other hurricanes, which were in $215 billion, and then Sandy and the drought year of 2012, which was about $130 billion. So again, the same description from 1980 through 2017. The average annual cost was for these billion-dollar disaster events was about $40.5 billion. In the last 5 years, it more than doubled at $84.1 billion. And again, exposure, vulnerability, but also some changes in the environment and climate change is playing a role in that as well. Next slide, please. Okay, 1 second, my computer just faded here. All right, let's go to the table as I get my computer back on. So this table, I presume you're looking at right now, shows the cumulative losses for all 238 different billion-dollar disaster events we have analyzed since 1980. And the cumulative cost of those events is almost $1.6 trillion. And 1 second while I log back in. The circles here denote some takeaways from this chart. The first is it does not surprise people that tropical cyclones, which are of course hurricanes, constitute the majority of the losses. About 55% of the total losses at $870 billion are from hurricanes. And the average costs for these events are about $22 billion each. But what does surprise people is the cost for drought. Drought is second cumulatively at $241 billion. So almost $250 billion since 1980 is due to drought, and he also has the second highest average cost at $9.7 billion. And the deaths with drought are of course from heat waves, which are sometimes associated with droughts, which happened earlier in the time period. Next slide, please. So wherever you come from in the United States, you can see that you have peril that you have to deal with, different disaster types. And so in the top left, you see drought is quite ubiquitous. In fact, most frequent in the for these events in the deep south and in the agricultural belts, and but really every place gets affected by drought at some level. Winter storms, of course, those are more related to nor'easters in the Northeast. Tropical cyclones from Texas to New England, you see that those events take place. Also, we track those as they go inland and become extratropical as they dump out their precipitation and cause a lot of damage inland. We track that as well. Bottom left corner shows that inland flooding, so non-tropical flooding, not from hurricane events, but from just massive flood events, those are, the water follows the floodplains and follows the rivers out to the major water bodies, and Texas, Louisiana have experienced a high frequency of that. Wildfires, particularly west of the Rockies, California by far has the most wildfire frequency and damage that we're sadly seeing now. And lastly, severe local storms. Again, this is tornado, hail, and straight line wind damage from thunderstorms. That's largely east of the Rockies. Next slide, please. So if you add all that together, you see basically the highest frequency exists in the south central and the southeast regions because they receive the highest number of these different perils. Texas, in fact, some might call it the disaster capital of the United States. There's a spatial bias there because it's a large space and it has a lot of exposure, but also it's really exposed to all of these different perils that we assess. But you see many states are really impacted by different disasters. In fact, all 50 states have been impacted by at least $1 billion disasters since 1980, including, of course, Hawaii, which was 1992 in Hurricane Iniki. Next slide, please. So this is a much more interesting slide, I think. It shows the cumulative cost, not the cumulative frequency. And again, Texas not only has the highest cumulative frequency that we just saw in the last slide, but it also has the highest cumulative cost. It's about $240 billion, and this is interactive, and you can look at this on the website. Florida would be number 2 at about $215 billion. But again, no matter where you head in the United States, you have some reason to want to reduce your vulnerability and adapt to changes and extremes because many places are impacted by a variety of hazards. One more slide, please. And I'd like to highlight, this is just 2017 data. So last year, the $306 billion from the 16 separate disasters. This is each state's cost from last year for these disasters as a percentage of that state's 2017 GSP, which is their economic output for the entire state. And you can see that by comparison, truly extreme events do have an impact on baseline economics, particularly if a state is hit over and over and over, like often happens perhaps in the Deep South, where the recovery just never finalizes. It just never can fully recover. And so this is just an example of one of these socioeconomic variables we've added to the product suite to let you explore annually or by event type how a state's economy is in relation to the losses for these disasters. And I think that's my final slide. One more slide, and yeah, here's some resources. The top is the link to the website, and there's some other peer-reviewed literature we've developed, and some great literature that goes into this in far deeper detail. With that, I think that's all. Thank you.
Thanks very much. A terrific amount of information and a lot of interest. Quite a few people wrote in asking to get copies of the slides. So I'll just say again that C2ES will be posting a recording of this webinar on our website, c2es.org. That's the letter C, the number 2, the letter E, the letter S. You should find the recording up in a day or two. In the meanwhile, Adam, I believe everything you've shown us today is available on the website listed at the top here, right? So interested people can go and get this data for themselves?
That's right, and you can also download data.
Terrific. So it's a great resource. I definitely recommend that people grab a screenshot of that, ncdc.gov/billions, if they're interested in more. I do want to make sure that we have enough time for Michael's full presentation and some questions. So with no further ado, let's turn it over to Michael.
Thank you, Ashley. I'm going to talk about attribution of hurricanes in particular, but in general. And But first I have to give a disclaimer that what I say today are my opinions, not that of the United States Department of Energy, the Lawrence Berkeley National Laboratory, or the University of California. Now what I mean by attribution is really quantifying, in this case, quantifying the influence of anthropogenic climate change, global warming, on individual extreme weather events. This is a rather new science, having been invented after the 2003 heat wave in Central Europe that was responsible for 70,000 excess deaths. First individual event attribution paper was published in 2004. The late Steve Snyder described climate science as a contact sport. And indeed, being an attribution scientist is a lot like being a offensive lineman. There's going to be a lot of hits because this can be controversial. So next slide, please. So there are many reasons to do extreme event attribution, but the most obvious one is when some big extreme weather disaster happens, the public wants to know, is this indeed climate change? And like I said, this is a science that has been developing rapidly. The State of the Climate report that was mentioned earlier has had a supplement for the last 6 or 7 years that is devoted to the extreme weather events of the previous year and trying to explain the human influence. And this has now become quite a interesting annual publication. The first one only had 6 events in it, and now it's 20 or 30 each year. So there are more and more scientists pursuing this. But so, the public wants to know, is this climate change? Next slide, please. So this attribution is really an exercise in causality. Statisticians have given us a causal theory. We borrow from epidemiology to use their language and their formalisms. And so imagine a 60-year-old man who has asthma, and all of a sudden you put him in a smoke-filled environment. What are the risks of complications? Well, obviously, there's a lot of factors. Family health could be one. His general health might be another. The amount of smoke, the severity of his asthma. And so causality is trying to untangle those. And so asking, is this climate change? Or conversely, something like, did climate change flood my house? Because of some flood, is a difficult and really not the right question to ask. But instead, we ask questions like, how has the risk of this particular weather event changed because of climate change? How has the probability of this event changed for a given magnitude? Or conversely, and this is really the same kind of question, is how did climate change affect the magnitude of this event at, say, a fixed probability? Next slide, please. So that's what we do, is quantify the human influence on very specific weather events. And so we have to consider 2 worlds. The first would be the real world with humans burning fossil fuels since the Industrial Revolution. And then a counterfactual world, so that's the actual world. A counterfactual world would be the same, except that humans didn't discover coal and oil and found their energy some other way. And this kind of experiment we can't actually do because we only have one planet, so we have to rely on models. And traditionally, one would use climate models. Climate models are large computer programs that simulate the motion and thermodynamics of the atmosphere, the ocean, the sea ice, the land surface, and biogeochemistry, and the influence of the sun and the volcanoes, as well as the human changes to the composition of the atmosphere, increasing carbon dioxide principally. We also can use statistical models. That's a rather recent development where we don't actually use the climate models. We just use the actual observational data. That's a different kind of causal theory. I won't get into the details of that. But again, it's not an uncommon thing to do in epidemiology. Next slide, please. So we haven't had any equations yet, and what scientists can give what kind of hour and a half session would be without any equations. So I have two. They're other simple ones. The first is defining what we might call probabilistic extreme event attribution, which is how has the risk of a particular weather event changed because of climate change. And so using this actual world and counterfactual world as simulated by the climate or statistical model, if we hold the event of the magnitude of the event constant, like a certain amount of rainfall or a certain temperature that actually is observed, how did the probability of that event in these simulations change when we went from the real world to the world that might have been? If we do the ratio of those, we call that the risk ratio. Epidemiologists would call it that. And so if the probability is, say, 10% in the real world and only 5% in the world without climate change, then we would say the risk ratio is 2. In other words, it's twice as likely for this event to have occurred because of climate change. Next slide. So flipping this around and holding the magnitude of the event constant, let's say we wanted to look at the 10%, the event with a 10% probability of, let's say, a temperature being reached, we can look at how that 10% event was in the counterfactual world that might have been, and we can just say the difference. And so, say for instance, the 10% event is 105 degrees in the current world and 102 degrees in a world without humans. We would say that this change was that climate change caused a 3 degree increase in that event. And of course, all of these attribution statements are incomplete without a full disclosure of the uncertainties. And in fact, that's where a lot of my research has focused, is trying to quantify those uncertainties. And the way I like to express these things is a very conservative way. And so I'll say statements like climate change increased the amount of rainfall, likely increase the amount of rainfall by at least 19%. And that's a statement from Harvey. And in fact, that's a very conservative statement looking at the lower bound of the uncertainty on this quantity here. Next slide, please. So we jumped into Hurricane Harvey prematurely here. I'm sorry about that. Mark Risser and I, a brilliant young statistician at Berkeley lab, looked at Hurricane Harvey with a statistical model, and we constructed this with two covariates to include the effect, the non-stationarity. One of these covariates was the logarithm of atmospheric carbon dioxide. That was the human influence. And then the other one is El Nino, and that's because we know that precipitation and, in fact, tropical cyclones depend on the phase of El Nino in Texas. And so we asked the question, after constructing the statistical model, using just observational data alone in the stations shown on the panel on the left, what would the precipitation of a storm of Harvey's rarity — Harvey was a very rare storm — be with 1950 values of carbon dioxide, but 2017 values of the El Nino index? And there we made the statement that the chances of this, so this is that first kind of statement, the probabilistic statement, the risk ratio, was our best estimate was that it was 10 times more likely because of climate change. And our conservative statement, this likely lower bound, was that it was increased by a factor of 3.5. So it was likely at least 3.5 times more likely to happen because of climate change. We also could talk about the precipitation increase, which I think may be more relevant or more accessible to most people. And we said our best estimate was that climate change increased precipitation by 38% in the tight, small ellipse that you see on these pictures, and with a lower bound of 19%. So it likely changed the amount of precipitation by at least 19%. Next slide, please. Now, confidence in a human effect on Hurricane Harvey's precipitation is quite high, and the reason it was high, it's just gotten higher, but for a reason I'll talk about in a minute. But it's high because there are 4 papers on this from independent groups using different methods and different data, and we come to the same basic conclusion. I told you ours, Gert-Jan van Oldenburg in the Netherlands wrote a similar statement that chances were increased by 3 times, which is close to our lower bound, and the precipitation was increased by 15%. The other one that's directly comparable is the one by Wang et al., and they wrote that precipitation was increased by 20%. Now, these numbers are all different, but they are within each other's confidence intervals, and so they, in some sense, are actually very similar. So at this point, if this was all we had, and this is all we had until tomorrow, we would say that confidence is high because we looked at this a bunch of different ways and we get the same basic answer. However, to really understand this, we have to have a physical mechanism for why these results have been found. The next slide, please. So tomorrow, Christina Patricola and I have a paper to appear in Nature magazine, and if there are any reporters online, I would ask you to respect the fact that this result is embargoed until tomorrow. If you are interested in writing about it, contact me and I will put you in touch with the laboratory press officer who will send you the press release. And there are certain things about the embargo that you have to know about. But this paper looks at 15 different storms and in detail in hurricanes Maria, Irma, and Katrina. And we looked at both changes in the current state of the climate due to in both the winds and in the precipitation of these storms, as well as a change at the end of this century under a much warmer climate. I call it the no policy scenario. For those of you who know, it's the RCP 8.5 scenario. So it's about a 3 or 3.5 degree warmer world than present day in centigrade. And the interesting thing here is we're seeing a consistent increase in precipitation. We do not see an increase in the winds. This is what I had expected, not yet, but it certainly does emerge as the climate continues to warm. For precipitation, you'll notice if you look at, say, Maria, which is the bottom one, and you'll see that the precipitation in a composite storm of all these simulations is not symmetric about the storm. It's a little higher at say 1 o'clock on this picture. If you look at the change, and it's a percent change, that part of the storm increases the most in the current climate change, the middle column, and indeed in the future climate change, under future climate change. And so this then tells me that there's a structural change in the storm that relates back to Harvey, because that part of Harvey was where Houston was. So Houston had the unfortunate circumstance of being in the place where it was raining the most. And so climate change, these simulations tell us that structural changes are affecting the part where it rains the most in the largest amount. And in fact, as you look at the much warmer world, you can see that the inner part of the storm is robbing moisture from the outer part. Now, this is a new result. We don't completely understand it, but it does explain these 4 previous papers for Harvey. Next slide, please. So some of you may have seen a statement we made about Hurricane Florence, which was, of course, devastating in North Carolina and parts of South Carolina. And in that statement, that was the world's first forecasted in advance attribution statement. We released a statement on Wednesday, and landfall was on Friday. We actually did the calculation on Monday night of that same week. And our statement was, we find that rainfall will be significantly increased, and the will is because it's now a future statement, whereas every other attribution statement up until this one had been done in a retrospective analysis. And we wrote, it will be increased by over 50% in the heaviest precipitating parts of the storm. So that would be that part of the storm that is raining the most in the previous picture. And we also wrote that the storm size will be somewhat larger, As I noted, this was the first statement made in advance of a storm. So it's sort of a proof of concept that this could be done by the National Weather Service or the National Hurricane Center in advance if that were something that was desirable. We're now going back to these and doing a retrospective analysis to be our own critics, and these results appear to be holding up quite well. Florence was the track of Florence was a very well forecasted storm, and in fact we used the same initial and boundary conditions as the National Hurricane Center, and we got essentially the same forecast as National Hurricane Center with a very different model, but the precipitation amount and the track were about the same, which is why we went public with it. The next slide, please. This is my last slide. So as I mentioned, the field's rapidly evolving. The first attribution study on a heat wave was in 2004. That was the Central European heat wave with the 70,000 deaths. The first seasonal flood paper wasn't until 2011 by Pardeep Paul, as part of his PhD thesis, also in Nature magazine, which was in England and Wales. And then in 2016 and 2017, the first short-term floods were analyzed in this way in the September 2013 events in Colorado. You'll notice that there was a 3-year lag between the events and the papers. That's because techniques had to be developed. And then Hurricane Harvey was the first storm analyzed in this way. And now we have the first forecasted attribution statement. And so what I'd like to leave you with is that precipitation in hurricanes has already been increased by global warming. We also have positive attribution statements for pretty much every heat wave that's going to occur from now on. And many kinds of other events, including floods and some certain types of droughts. And so my conclusion is that dangerous climate change is here now, and it is not something in the distant future for our children or grandchildren. It is our problem right now. So I think that's my last slide. There's an email contact on the next one. So thank you very much.
Thank you, and I'll leave your email address up for a few seconds longer. If oh, apologies here, the slides have run away from me. And sorry again if anyone got whiplash going back and forth on Michael's slides as they were advancing a little quickly there. So if anyone did want to reach out about that study coming out in Nature tomorrow, here is Michael's email address. I had promised you time for questions, but I'm afraid that that's a promise I'm not going to be able to keep, as we do want to be respectful of everyone's time, and it's been our 90 minutes here today. I'll remind everyone again, the recording to this webinar will be posted on our website, c2es.org, up in the next day or two, and you'll find a link to the recording here for the slides. Many of the slides here, though, and in particular those slides from NCEI, are available online, so you can get that data and use it as you need. I will leave on a note of one of the questions that came in about taking in all this information and rapidly evolving science as we're seeing. What are we supposed to do with this? How can resilience planners, how can companies, how can the military, how can interested parties take this data and incorporate it into their resilience strategies and their continuity plans? There is data available to you. We've seen a good bit of it today, which would be my answer, is to use the data the best you can. However, this is a topic that we at C2ES are studying pretty actively and working to understand better. And for anyone interested in these questions, particularly in the private sector, about how do you use this data, I'll note that the next webinar that C2ES will be hosting will be after Thanksgiving on November 28th. That webinar is called A Practical Guide to Climate Disclosure, and we'll start talking through some of that usage of data, particularly as it applies to implementing the recommendations of the Task Force on Climate-Related Financial Disclosures, the TCFD process, for those who are familiar with that term. So that may be of interest, but do stay tuned to all the work that we're doing at C2ES. And with that, I'll just give a final thank you to the experts who joined us today, sharing this information and putting us all at the very leading edge of our understanding of the climate change that is indeed here and now. And thanks to all of you for tuning in. Have a good day. Bye-bye.